We took a good look at what it means to multiply a ring element by a positive integer, by a natural number. Now we're going to look at non-positive multiples of ring elements. First, we're going to define integer multiples of ring elements by non-positive integers, and then we're going to prove a theorem using that definition. So as before, let's let R be a ring and let X be an element of R. First thing we want to know is what does it mean to multiply the ring element X by the integer 0? Well, the most reasonable thing we could say is, well, it has to be an element of the ring, and we expect it to be the 0 element. Now, I do want to point out that there are two different zeros in that equation. That 0 on the left is the integer 0, and the 0 on the right is the 0 element of the ring R, the additive identity in that ring. So now let's see what happens when we multiply it by -1. Let's start with our first negative number. Well, based upon our experience of multiplying other things by -1, it makes sense that -1 turns any element into its additive inverse. So it makes sense to say that -1 times x is equal to -x. And I do want to actually point out again that those two negatives have very subtly different meanings. That first negative belongs to -1, the integer, so that's the additive inverse of the integer 1. That negative on the right-hand side is the negative of the ring element x. That means that -x is the additive inverse of x. For -2x, it makes sense that that should be two negative x's, right? -x plus -x. And that is, by definition, 2 times -x. For -3 times x, it makes sense that that should be -x plus -x plus -x, 3 of them, right? And by definition, again, when we add something to itself 3 times, that is 3 times -x. And I should note that 2 times -x and 3 times -x, those are quantities that we have already defined. We've already defined what it means to multiply any ring element, whether it be x or -x, by a natural number. So this suggests the following definition. If R is a ring and X is an element of R, we define for any element n in the integers where n is less than or equal to 0, that, well, if n is equal to 0, 0 times x should be the 0 element of R. If n is less than 0, then n times x equals, well, this is going to be a little bit of a tongue twister here, because remember that n is a negative number, so think of n as being like -1 or -2 and -3 above. The first thing we did was turn that into a positive number by taking its negative, so n is a negative number, n is a positive number, and then we multiplied that by -x. And again, I do want to point out that if n is less than 0, n is going to be greater than 0, which means that saying what n times -x is, we already know what that is because we've already defined what it means to multiply by a natural number. All right, so we can use the definition of multiplication by natural numbers for the second part of the definition, right? The right-hand side of the equation. And that tells us what the left-hand side of the equation is, multiplication by a negative integer. All right. So let's use this to prove a theorem, and actually this is going to be pretty much the same theorem as we proved in the last video, except we're going to expand it from the natural numbers to the integers. So if x and y are elements of a ring R, if n is an integer, then n times x plus y is equal to nx plus ny. All right, so what we're going to do is we're going to consider the cases of n greater than 0, n equals 0, and n less than 0 separately, and this is actually going to be very common for us to do. And for the case n greater than 0, we've already proved that, right? That means n is a natural number, and that was proved in the previous video. So if you forget how to do that, all we did was prove it by induction using the recursive definition of multiplication by natural numbers. That leaves us the last two cases where n is equal to 0 and n is less than 0. We'll start with n equals 0. That's usually the easiest one. For n equals 0, what the definition of multiplying by 0 is, well, anytime we multiply by the integer 0, whatever the ring element is, we end up with the 0 element of R. So 0 times x plus y gives us the 0 element of R. If we look at 0x plus 0y, 0x is equal to the 0 element in R. 0y is equal to the 0 element of R as well. And when you add those together, you end up with the 0 element of R. Since both 0 times x plus y and 0x plus 0y give us the 0 element of R, that means they're equal to each other, so 0 times x plus y is equal to 0x plus 0y. So that wasn't too bad. For n less than 0, we're just going to use the definition of multiplication by negative integers. And remember that definition by negative integers is not a recursive definition, so we don't have to use any induction. We can literally just use the definition. So if I'm looking at n times x plus y, by definition, since n is a negative number, that is negative n times the additive inverse of x plus y, which is negative x plus y. Now we're going to want to do a little bit of simplification. We actually saw what happens when we take the additive inverse of x plus y. That's equal to negative x plus negative y. If you remember, you added negative x plus negative y to x plus y to give you 0, and that's what proved our result. But you don't have to say what that proof is. I was just reminding you. You can just cite the fact that we proved it. So that means if I want to look at n times x plus y, I can substitute that in. I get negative n times negative x plus negative y. Now, keep an eye on that negative n. That is a positive integer. That's a natural number, right? Since n is a negative number, negative integer, that means negative n is a positive integer. And that means since we've proven this result for the natural numbers, we can apply that result to negative n times negative x plus negative y. Right? Our result before said if we take a natural number and multiply it by the sum of two ring elements, no matter what those ring elements are, the sort of pseudo distributive property holds. So using that result, we have negative n times negative x plus negative y equals negative n negative x plus negative n negative y. And so remember, those are all equal to n times x plus y because n times x plus y was equal to what was on the left-hand side of that equation. So now all we have to do is use the definition of multiplication by negative numbers to finish this off. Because if you remember, right, that negative n times negative x, that looks familiar. Well, yeah, that is exactly the definition of nx. When n is a negative number, which it is, nx is equal to negative n times negative x. And when negative n is when n is a negative number, that means n times y is equal to negative n times negative y. So we can just substitute those back in, and that gives us n times x plus y is equal to nx plus ny, and that's our theorem. So I do want to give you an overview about what the general process is when we go to prove theorems about integer multiples. Usually there's a three-step process. The first step is just concentrating on multiplying by natural numbers. For that one, we have to use the recursive definition of multiplication by integers, and that usually means that we'll have to prove that theorem by induction. So once we've proved it for natural numbers, then we look at the non-integers that aren't natural numbers. So that's probably starts with 0, or at some point it has to go through 0. So then we prove the theorem for when the integer is 0, and then finally we have to prove the theorem when the integer is a negative number, and that just means that we have to use the definition of multiplication by negative numbers. And usually this means that we have to use whatever result we just proved for the natural numbers, for the positive integers, in order to finish up that case. All right, so it looks like you are ready to work on the in-class activities. The name of the PDF file is integer multiples -integers.